Welcome, Cavaliers. Can I get a go blue? Go blue! One more time, go blue? Go! I love it. All right, I have a really special treat for you guys today. Joining us is Dr. Lawrence J. DeLucas. He is the principal scientist with Aerospace Corporation. He's a retired NASA astronaut who went up on a mission. It's NASA Space Shuttle mission STS-50 as a payload specialist on Space Shuttle Columbia back in 1992. I was a senior that year. Dr. DeLucas holds a Bachelor of Science and a Master of Science in Chemistry. He has a Bachelor of Science in Physiological Optics, a doctorate in optometry, and a doctorate in biochemistry. So I'm fairly comfortable saying he's qualified to talk to you all today. But the really neat thing is, he's traveled over 5.7 million miles in outer space. That's 221 Earth orbits, logging over 331 hours in space, which is incredible to think of. I've got miles and miles of questions for myself. But without further ado, I want to just mention his daughter Katie's in the house. So let's welcome Dr. Lawrence DeLucas to the stage.
Since 1992, I've spoken and visited probably 300 different schools. This one is number one. Unbelievable place in the state. I want to start by kind of telling you where I was at, when I was a little bit younger than you and your age, and how I got interested in science. So how it all started. So when I was in grade school and high school, I was on the basketball team and the baseball team. I did like astronomy, but never thought I'd have anything to do with NASA. We ended up building our own telescope in high school. We ground the mirror. It was a 12-inch mirror. But anyway, and what really got me interested in science was my chemistry teacher in high school. He made chemistry so much fun. I guess because of my interest in sports, I've always been very competitive. And what this teacher would do is do an experiment on a Monday, and then the next time we met, usually I think we met 3 times a week, on Wednesday, he had everyone's name on a 3x5 card. And he would shuffle the deck and pull out one card. And if it said Larry DeLucas, I had to go stand up in front of the class and explain the results of that experiment, why it worked the way it did. Back then, we couldn't Google anything. We didn't have the ability to look on internet, so we all could go to the library. We could work in teams to figure the experiments out, but it was just a lot of fun being able to figure this out on our own, and it sort of began teaching me how to think for myself, and that's very important in science. And so when I started college, I thought, well, the only thing I know I liked was chemistry, so I'll major in chemistry, and that's how I ended up getting the degrees that you heard about in college. But again, I started out in college thinking, I remember the first, back then, if you did well on an exam, you could skip the first, and it turns out for me, I skipped the first year of chemistry in college. So I started in organic chemistry, and I thought that teacher was the smartest person I ever met in my life. And I did real well on the first couple exams, and I was kind of a nerd. I sat on the front row, no offense, you're not nerds. But anyway, I was on the front row, and after one of the classes, he walked up to me and he asked me if I wanted to come work for him. And I needed money to help pay for school, and so I ended up working 20 hours a week for this organic chemistry teacher. Made a lot of mistakes in his lab. But again, as time went by, I worked for him for 2 solid years, but finally I started understanding what he was after. He was a polymer chemist, and I started suggesting things that every once in a while my suggestion really helped. And that gave me a little more confidence that maybe I could do this science stuff. So I really started, thanks to teachers, It really is what allowed me to continue in science. Because I really, in high school, I thought, you know, I'm probably going to be a basketball coach or a baseball coach because I love sports so much. Well, after all that, I call it my lucky trip to the gym. I got involved for my doctorate in biochemistry in a field called crystallography, where we grow crystals, we expose them to an X-ray beam, usually at a synchrotron facility. So these take up a city block. You spin electrons around in a circle, you wiggle the electrons, and it emits a radiation, and then your crystal gets exposed to that radiation beam, and you can determine the structure, where every little atom is in the protein within thousandths of an angstrom. But the problem was, back then, because we're talking about 1980, 1979 actually, in the United States, the only place where they were trying to do protein crystallography was the university I was at, University of Alabama at Birmingham, Georgia, University of Georgia, MIT, and Caltech. Pretty much no one else was doing it. It was so new. No one knew how to do it. And so I looked around. There were people that had their PhD degree and couldn't find a job because no one was doing this. No pharmaceutical would do it because to determine the structure of a protein back then took 15 years. So, you know, it just wasn't very useful. And so I was ready to drop out of school after 1 year of working on protein crystallography. And my lucky trip to the gym, I went to the gym to play basketball one night, and I knocked over this older gentleman. His glasses came off, and I helped him up, and he started talking to me. It turned out he was the dean of the School of Optometry. And I told him what I was doing, and I said, but at the end of the semester, I think I'm going to drop out of school and just try to find a job somewhere, because I know I'm never going to get a job as a protein crystallographer. And he said to me, Larry, in the visual system, there are many proteins involved, and we don't understand how the visual system works. You go get that PhD degree in crystallography and go to optometry school and become an optometrist, and I'll hire you immediately. So I applied to optometry school. You know, it's funny, when you apply to a professional school, the first question, whether it's for a physician or a dentist, the first question they ask you is, why do you want to be a doctor or an optometrist? So they asked me that question, and I said, I don't. And, you know, the committee was shocked, and I said, you know, I want to do this, and I'll do research about vision and all the proteins involved in vision. And it turns out they accepted me, and I ended up getting that optometry degree along with the PhD degree. I did them simultaneously. Almost killed me, but at the end of that time, immediately that dean hired me on the faculty. So I got that job that I needed. So anyway, that's how I got involved. And so here's, for those of you that aren't familiar with the technique of crystallography, we first have to grow single crystals, like you see way over there on the far left. And then they're exposed to an X-ray beam, and then you get a diffraction pattern of peaks, like you see here. Today, it's all electronic. By the way, to determine that structure, that protein you see on the left, every one of you have that protein in your body. It's called purine nucleoside phosphorylase. It's very important. When it's not working right, it causes a devastating cancer called T-cell lymphoma. We determined that structure. Then in the active site where that protein works, we developed a drug that would block it. And today it's a drug on the market in Europe, and hopefully soon it will be in the United States. It takes so long to get these things approved, especially for rare diseases like this one. But anyway, today, if you have a crystal, once you have that crystal, you go to a synchrotron, you collect the data, which takes about 5 or 6 minutes, and that night you see the structure in high resolution. So now all drugs that are made today, if we can get the structure, they use it. It's called structure-based drug design. So all the drugs for HIV were designed using structures of the proteins that are key in the virus. Anyway, that's the technique. Well, what does space have to do with any of this? If you don't have a high-quality crystal, so what that crystal is the protein repeated over and over, like a row of bricks on the wall, but in 3 dimensions. So literally hundreds of thousands of copies of the protein are in one of those crystals. They have to be perfectly aligned. If they're misaligned, when we blast them with the X-ray beam, we don't get high quality data and we can't determine the structure. So, again, what does space have to do with it? Well, here's one time, and I think everyone will identify with this. Here's one time when a politician did something useful. Doesn't happen very often, does it? But anyway, we had a senator in Alabama. His name was Howell Heflin. And he said, we have all these scientists at the university, and we have all these scientists and engineers not far away at Marshall Space Flight Center, just about an hour and a half drive away. And they have never gotten together to share what they're doing. So he said, let's organize a conference and let them all talk about what they're doing, and maybe there's something better we can do together. So this one scientist at Marshall Space Flight Center showed that image you see over there on the left. That's a crystal, that block-like area right there is a crystal. And he's using an optical technique that lets you see motion in the solution. As a protein crystal grows, now that's a salt crystal, not protein, but doesn't matter. As it grows, lighter molecules are floating up, heavier ones are sinking. It's sort of like when you heat a pan of water. Now it's not that turbulent, but that's what's happening. So now, as the molecules come in to form the crystal, they're going to come in sometimes upside down, twisted in different orientations, and they have to have time to get perfectly aligned before another one comes in. Otherwise, they get trapped in misalignments, and again, that ruins the quality of the crystal. And so he showed that, and then he showed the slide you see on the right. The square at the bottom is that same salt crystal grown in space. Now you can't use an optical technique to look at flow, because in space there are no lighter and heavier molecules. There's no flow. The only thing that makes molecules move in space in a solution is random diffusion. So all molecules just naturally are vibrating, they bump into each other, and they make their way to the crystal. The difference is it's an order of magnitude, sometimes 2 orders of magnitude, slower how fast they move. And so now when they get to the crystal, again, they may be upside down, but they have time to bounce around and energetically find the best position, based on all the interactions, ionic interactions and so forth, to get perfectly aligned. And so he showed those 2 slides, and then he went into his pocket, pulled out a Ziploc bag of a crystal of a salt called triglycine sulfate that he grew in space. And I'm not kidding, it was the size of my fist. Because everything's perfectly aligned, the crystal keeps growing. When they become misaligned, pretty soon the next crystal can't come in and bind, and so the crystal doesn't grow. And so he talked about how you can get much larger crystals grown in space. So I said, wow, we have to do this with proteins, because they grow the same way you would grow a salt crystal. And so I learned right then, as I started to think about how to do this in space, space makes you think differently. And so on Earth, the way we grew crystals back then, you see those little droplets? They're hanging upside down from a cover slip. And the droplet is usually 1 microliter in volume. Down below is a reservoir of 1 milliliter, so 1,000 times more solution. There's more salt down below than in the drop. The cover slip is sealed with grease around the edge there. Once you seal it, because there's more salt down below, equilibrium has to be established with respect to the salt concentration. So water comes out of that little tiny drop, diffuses down into the reservoir below. The drop gets smaller, pushes the protein closer together. If the pH is right, the ionic strength, all these different conditions, you get crystals. So that's the way we do it on Earth. Now, if we did that in space, the solution down below will wick up the wall, go across the cover slip, and touch the drop. That would ruin the experiment. So in space, the attraction of a liquid for a surface dominates everything. So I knew we're not going to be able to do that. So I designed instead this piece of hardware. So at the very top, the little kind of glass area you see coming through the windows are glass syringes. The protein was in there. The solution, the 1 milliliter solution, is behind the steel plate on the other side. And you know the pens you all write with, the felt pens? That material is called Chromex. It's used because it really has a high surface attraction for any aqueous liquid. And so I thought we could soak that with liquid. It will hold the 1 milliliter so it won't, through surface tension, wake up and touch the drop hanging from that glass syringe. So that's what I designed. And then it turns out if you have an experiment going on the space shuttle, they let you watch the experiment, the shuttle take off, right with the spouses of the astronauts. And so I was as close as you can get to watch this. And there was the launch in 1985. So my experiment was on that flight, and I'm standing there, and I don't know why, I've never cried at a funeral. I'm very sad, but I just don't cry. I think I only cry when I'm happy. But anyway, I'm watching this thing take off, and the first thing I saw was the fire and smoke. But the sound hadn't reached me yet. And then all of a sudden, when you're that close, the ground started to vibrate. I got hit into my chest with a shock wave from the sound, and I started crying. And I turned to my wife, who was with me, and she was crying. There were all these television reporters from the university there. They were all crying. And then I said to everybody, someday I'm going to fly on that. And it just hit me. It became a quest. I had to experience what it would be like to get on that rocket and go into space. And so I started trying to see how can you get selected, and that was a process. It took 6 years, but here's what we saw from that first flight. You see the little white specks in the droplet hanging from the tip of the syringe. Those are crystals growing of a protein. On Earth, they would either be lighter in density or heavier and sink to the bottom or float to the top, and they get stuck together. Well, protein crystals are anywhere from 30 to 95% water. You can't touch them. They'll mush and fall apart. But in space, wherever they start to grow, they stay right there. And so we had all these beautiful, perfectly formed crystals that came back. And I didn't just fly proteins, in my own lab. I flew proteins for pharmaceutical companies, and I'll just give you one example. On the left is the best crystals they could grow at DuPont Pharmaceuticals of a very important protein they were working on to develop a new insecticide. On the right, that's the crystals that came back from space. It was examples like that that made NASA start this huge program in protein crystallography on the space shuttle. Japan followed suit. Russia, even China started doing it with their Long March rockets. And so it became a huge program all through the space community. So after 6 years of trying to get selected, that is me on the far right. You see, when you go to space, it makes your hair turn gray. And so I don't look quite like that. That's a joke. So anyway, there were 7 of us, 2 women and 5 men on the flight. So the first year, I didn't know if I was going to get to fly. I had to compete with one other scientist. It was actually a scientist that got his PhD at MIT. And so we went to 31 different locations. There were 31 different experiments on this flight. And the principal investigator for those experiments each had 1 vote. So we would go and spend a week at University of California, and in classrooms they would teach us about the theory. Then we'd go in the lab and we'd do their experiment, and they'd film us to evaluate how well we're doing. And we did that for a solid year, going to all these places. And at the end of the year, then I had to take an oral exam. So I'm sitting in a chair, and 31 scientists are in a semicircle around me. Now they could ask me all about the theory, anything about the experiment. My exam took 4 hours, and then the person I competed with went next. So I was in an airport. Back then, the cell phones were that big. And I got a call on my cell phone right before I got on the plane to tell me that I was the one they selected to fly. And right there in the airport, I burst out crying again. That's how much it took out of me. But it ended up, it was really worth it. So anyway, you can see we had to learn all types of combustion experiments that we did. We did a lot of fluid dynamics experiments, how liquids would react on different surfaces. We also spun liquids with sound to look at how heavenly bodies spin in space. We did 3 types of crystal growth. Of course, I was the principal investigator for proteins, but also zeolite crystals are used as one of the final processes to purify gasoline. The larger you can grow those crystals, the more efficient that process can become. And of course, you know all about all of the ways we use semiconductor crystals. So those were in a long ampoule where we would melt the metal and then create a more perfectly formed crystal, semiconductor crystal in space. Because I was and still am, I think, the only eye doctor ever to fly in space, NASA decided, let's take advantage of this. So I had everything you need to give a complete eye exam, and I'll never forget, I was allowed to dilate 4 other crew, not the pilot and commander, but everyone else. And the first time I looked in their eye at the retina, everybody was bleeding. They had what's called petite hemorrhaging. When you go to space, your fluid shifts upward. You get kind of a puffy face, and the extra pressure causes little capillaries in your retina to start leaking blood. So I, imaged that and downlinked it. Didn't think about, much about it, because after we landed, within 2 days, most of that resorbed and everyone looked normal. But I should have thought, what if we stay for 6 months like we do on the space station? We now know from studies that have been done, astronauts that stayed there before we learned how to treat them for 6 months, 5 of the 6 astronauts they looked at had glaucoma, which is a permanent loss of vision in your periphery. And so it's something now we treat when you go to space and stay for long periods of time. Anyway, and we also did experiments like an ant farm for small children. So after the first year, I moved to Houston with my family, and now it really becomes a lot of fun. I had to learn all about the mainframe computers for the space shuttle. 1960 technology. We even, for some of your teachers may know, we had a computer called a PDP-8, where you actually have to put a ticker tape in to get it to work. So really old-fashioned. You wonder, why didn't they upgrade it? Well, the commander told me, number 1, these work. Number 2, it would cost a lot of money. Now, the computers for experiments for the science were always the latest, but not what operates the shuttle. Had to learn all about the orbital mechanics of how we were going to fly the shuttle. I had to do strenuous things like rappelling off the top of the shuttle in case there's an emergency when we land. Had to take all kinds of medicine to see what I could tolerate. 78% of male astronauts that fly in space spend usually the first 2 to 3 days barfing. It's a little bit better for females, about 70%, but still not very good. So they want to know what you can tolerate. I actually was one of 2 astronauts on our flight. I not only did not feel sick, I gained 3 pounds in 14 days. But anyway, we have to learn all about fire safety. So they actually would build a fire. Probably, it was a lake about 4 times the size of this auditorium, and I had to put that fire out. The whole lake was on fire, and so much fun doing things like that. But anyway, and then every once in a while we'd go back to Marshall and kind of review the science that we had been learning. So that was the 2nd year, and what I always like to say, here was my typical day that 2nd year. I got up at 6 in the morning. I hate to run, but I knew I had to be in shape, so I would usually run a mile. And then I'd get ready for class. Class started at 9 o'clock, so I'd eat breakfast, go to class. At noon, we'd finish class, and the crew, not the pilot and commander, but all the mission specialists and payload specialists, we would run together 6.4 miles. It's the track around Johnson Space Center. And then we had to be back at class at 2 p.m. We go back to class, 2 to 5 we're in class. Then we go home from 5 to 7, can eat dinner with our family. At 7 o'clock, we had to go back. Now we put on the orange spacesuit, and we do a lot of physical training in the neutral buoyancy tank, a lot of different things we would do. And usually I got back home at 10 p.m. that night. I never felt tired. I was so excited what I was learning and what we were going to do the next day. It was for me like, being at Disney World the whole time. Just a lot of fun. Anyway, so part of the physical training, what if we're on the gantry ready to get in the shuttle and a fire breaks out or if something's going to explode? There's a zip line like you see here. Now it's not a seat, it's a wicker basket. 2 people can get in it. you hit the Pelican clip and you go down the zip line into that sand dune. There's a big sand trap down at the bottom. But, you know, everyone gets a nickname when they fly in space. You know, we had one pilot that has set all kinds of records in experimental jets with the Air Force. His nickname is Mad Dog Me. My nickname, unfortunately, was Which Way, because I have no sense of direction. I got lost in training all the time, and I'll never forget when we got in that and we got down to the sand trap. You know, what if there's an explosion? We could still be hurt from shrapnel. And so we get in that U.S. tank that you see right there, and I have to learn to drive that tank away. And I was with the commander, got in the tank, and I said, Dick, where can I go? And he looked at me and he said, which way? You're in a tank. This time it doesn't matter where you go. And so you see the trees in the background there. I drove right into it, just knocks them over. So I had fun just driving right through the forest. It was a lot of fun. So we also go to Brooks Air Force Base, and they spin us around in the centrifuge. Now it's a swinging bucket. So once you get in, your seat swings out. And so you're taking the extra G's through your chest, not head to toe, like a pilot would. So we do that because on launch, you know, I'm looking straight up and we take the G's into your chest. And so the shuttle profile is only 3.2 G's, but it is sustained for about 5.5 minutes. So first they make you go through that. So you're taking 3.5 G's or so for about 5 minutes. But then after that, in my ear, the guy running it said, Larry, you want to see how tough you are? So it became a competition, right? And so they go faster and faster. When I want them to stop, I have a little button. I could push the button to tell them to stop. Well, at 6 G's, it had squished all the blood out of my retina, so everything went black. I couldn't see. At 8.3 G's, I didn't want to push the button, but they saw my eyes were starting to roll into the back of my head. And so they stopped it. But I turned out I was second. I beat everyone but the pilot. I didn't beat the commander. And then after I finished my flight, about a year later, I became the chief scientist for the International Space Station. So I had to work in NASA headquarters in Washington, D.C. And at that time, John Glenn, one of the original 7, was a senator. So I got to know John really well, and we went to dinner one night, and I wanted to see, did I beat John Glenn, right? Because that'd be great to tell you. So I told John, you know, I did 8.3 in the centrifuge. What'd you do, John? And he didn't want to hurt my feelings, but, you know, I'm a very humble man. He's passed away now. But he said, well, Larry, actually, I set the record for NASA, 16 G's for 40 seconds. So I now know that's the right stuff. There's John on the second one. He was 80-some years old. And I must be the wrong stuff. But anyway, we also have to do abort training. So that's us practicing. If there's an abort, we have to open the hatch. It actually blows off the shuttle with explosive bolts, and we jump out. And then you hit the water. That's me. In my backpack, I have a little raft like you see there. So you pull it out, and you can either blow it up with a CO2 cartridge or just with your mouth. And then you get in it. So I'm practicing right now in a swimming pool, but then I had to parachute into the ocean off the coast of Miami. Once you hit the water, you blow up that raft. You're all by yourself. You cannot see land. You can't see any other crew. You're in shark-infested waters, and I stayed out there for almost 14 hours. They don't give you any food in your backpack. They give you a little water packet, so if you need to drink something, you got a little bit of water. But NASA, you know, is pretty considerate. If you're really hungry, they give you in your backpack an expandable plastic fishing pole. So I wasn't about to try to fish in shark-infested water. So I just starved for the 14 hours, and then you vector a plane to come find you. Once they do, a helicopter comes and lowers this kind of big sinker. You grab it, and they pull you up into the helicopter. Again, I just love doing stuff like that. A lot of fun. That's me in the back seat. I'm not a pilot, but I got to fly the jet in restricted airspace and had a lot of fun doing that in these T-38 jets. Now, this jet is a special jet. It has extra steel in the wing and the tail. It's called a KC-135. It climbs up to, 40,000 feet, and then they just turn the engines down so it's falling at the rate that gravity pulls you. As you know, if you do that, inside the plane, there is no gravity. And so then they have to pull out. So you have 20 seconds without gravity. When they pull out, everyone's pulling 2.5 times their body weight, 2.5 G. So you're stuck to the floor, and they just keep doing one parabola after another. You don't want to eat anything before you get on there. They call it the vomit comet for good reason. And this is me wasting taxpayer money. Most of the time, I'm strapped to the side, testing hardware, even gears without gravity. Sometimes you have to have a spring to make sure the teeth are fitting properly because you won't have the advantage of gravity keeping even two gears closely together. Anyway, had a lot of fun. I flew on that jet probably more than any scientist because of all the experiments I ended up doing in space. I would always test my new hardware before I flew. That's me the morning of the launch, not smiling. I'm thinking about what I'm going to do. According to the Air Force, the chance of a space shuttle exploding on launch was 1 in 26. According to NASA, 1 in 78. Turned out NASA was closer to the right numbers there. But anyway, so now let's see if we can get this to work. The shuttle tips 10 degrees, and then when it swings back straight, that's when the solids go off about 10 seconds later. And the first thing you always see is the shuttle would turn. It's called the roll procedure. That's because there's windows on the very top roof of the shuttle, and the commander's looking through those to see where, if we had an early abort, he could come down and land. So at this point, you're being squished into your seat, and soon, within about a minute and a half, we throttle up, and everyone is just trying to breathe for about the next 4 or 5 minutes, trying to get air into your chest. So the solid rockets now are going to explode off the shuttle, and now we're just using the three main engines. So the total flight from ground to get into space and orbit took 8 minutes and 43 seconds. There goes the solids. And now we're some 250 miles above Earth, and we're about to go over a portion of Saudi Arabia, and the little dark circles that you're going to see are irrigation fields. These are the Andes Mountains. I told NASA when I became chief scientist, oh, by the way, you see the light blue? That's our atmosphere. From space, it really looks like we're surrounded by a sheet of paper that we all have to share and breathe together. It makes you think how important it is to take care of our environment. So, there's the Himalaya mountains. So we're traveling at 17,500 miles per hour, and we make an orbit of Earth every 90 minutes. So obviously that's the moon, but that's magnified 15 times. So here I'm an amateur astronomer, very amateur, but I asked the commander what it was, because I'll show you in a second. That's magnified 5 times. We're going to go back once more, and I'll show you the way it looks. And the reason, it's basically an optical illusion. You have that big ball, the Earth, and then the moon, 240,000 miles away, it made it look like a planet. So here's the way it really looked. Isn't that something? I thought it was a planet. So my commander, when I asked him what that was, he couldn't believe I was an amateur astronomer. So we spent, a lot of time. I took 18 geography courses, but still every once in a while you would see vegetation in some of the islands that was dark blue, and it looked like that was the water instead of the water itself. It just depends on what was down there. When I flew, we had just finished the first war with Iraq, and at night, well, in the daytime, everything in that area, you know, looked beautiful, but at night, you could still see the fire burning in Kuwait, in the oil fields. It's just a strange feeling to see all these countries, no lines in between them, so close together, and yet people were down there not living together peacefully. So we get a sunrise or a sunset every 45 minutes. You usually don't see much more than that because it bleaches the camera. But again, NASA should fly a poet or a writer to tell you how emotional you feel looking down at the beauty of Earth. So I was always, interested in crystals, and that's our urine sent out of the shuttle. And when you send it out, it immediately freezes, and you get these beautiful crystals that are often different colors. I couldn't wait till we did another urine dump. But now we had incredible cameras, and I'll show you this. There's the moon again, really amazing. But we're going to focus in on the island of Japan and Mount Fuji, and we're going to zoom in on it. This is not a defense mission where they had much better resolution, telescopic type resolution, but there's Mount Fuji. Okay. When you get up there, that's the first thing I saw, the state of Florida. And I peered my head, I could see most of the United States just peering back and forth. But again, the Earth is only 250 miles below, so it's this huge ball below us. So I said surface tension dominates. Well, when I flew to drink liquid, it came in a bag, a flexible bag. You put your straw in the middle, and you start drinking orange drink, and what happens? Well, as soon as you start drinking, the rest of the liquid sticks to the wall, so you have a big air bubble in the middle. So I had to point my straw toward the wall and squeeze the bag to get liquid where my straw was pointing. Well, a scientist at Portland State and another astronaut, Don Pettit, said, let's take advantage of surface tension and design a space coffee cup. And so here's what they came up with. Well, just as an example first, that's Don Pettit. And that liquid, it's water, on his fingers, the surface between his two fingers and his mouth on the other side, as he sucks the water, his fingers pull the water because the two inside surface of both fingers pull the water through that little gap into his mouth. So based on that, they said, we can design something, and they came up with this design. So that is the first space coffee cup. It's wider on the far end, gets more narrow, the walls, as you get toward the bottom, and then even more narrow as you get to the spout where he's drinking. So as the walls come closer together, it pulls the liquid right into. Now the guy on the right forgot he's in space. He tips his head back. That doesn't do a thing in space. But you see how it's designed. It's wider on that far end, and you can see 3D. It just perfectly pulls the liquid. So that was the first one. Well, they said it's not very attractive, so they came up with a new design. Oops. It's this one. And they came up with that. You can see it's wider on one end, but then they said that's not all that great, and they came up with that one on the right. So, you may ask, why doesn't the liquid come over the edge and go outside? If you have a sharp 90-degree corner, then the liquid is called a pinning edge. The liquid won't go over that unless you shake it. And so the liquid goes down into that brown trough where the walls are closer, and then the narrow kind of trough area pulls it up into that area where you put your mouth over that lip, over the end of, over that whole end there, and it just feeds you the coffee. So today, we drink liquids on space station that are designed in containers like you see there. Well, that's me on my mission. I had to grow crystals, do a lot of combustion experiments in that enclosed environment right there. It's a little kind of short cabin to do everything so you don't let anything come out and hurt someone. So as an eye doctor, I was always curious, why do people get so sick in space? How many of you, raise your hand, if you're reading a book in a car, you start to feel sick? Look at all the hands. Okay, I'm going to help you. So in your ear, you have crystals that give you your sense of balance. Those crystals are connected to nuclei in your brain that are connected to another set that control the movement, your extraocular muscles, movement of your eyes. The problem is it's not coordinated. So when you're in a car, those crystals in your ear are bouncing in different directions. So your eyes, you can't see it. It's called a microsaccadic movement. They're moving in different directions like that. So if they were moving together, some people still get sick, but it's a lot easier to tolerate that. But that's not what happens in a car. They're moving differently like that. So how do you fix that? You patch one eye. And so to test this, I had this idea. This is going to stop people from getting sick in space. When you go to space, those crystals are floating in different directions. So I thought, we could all wear eye patches. But to test it, I took about 12 people. They were crew trainers in a van. We drove from Huntsville down to Cape Canaveral. I made them all, you don't wait till you feel sick, so they wore the eye patch from the beginning and read sometimes for 3-4 hours, and no one felt sick. I had done all these studies as an optometrist where we spin people in vestibular chairs, and I knew if you patch one eye, you're going to do a lot better, even in a chair spinning around. So I proposed to NASA that we all wear eye patches on launch. And I put this big presentation with all the data I had collected and things in the literature. The last thing I said was, why do you think the pirates wore eye patches on the ocean? Maybe that's why they said no in the end, but they did let one person wear the eye patch because he had flown before and got very, very sick in space. And so as a medical procedure, he wore the eye patch. We got up in space and he barfed his guts out for 3 or 4 days. So it didn't work up in space, but when we're coming home, I'm down in the middeck, and if you turn your head like this, everything is spinning. If you do this, it's flipping like that. If you're tilted, it's flipping like that. If you patch one eye, so I'm down in the middeck doing this, there's no spinning. Our pilot is a rookie. He had never flown before, Ken Bowersox, and he has one job when you're coming into land, because the commander's landing it with the stick. The pilot, landers, has to press the button to lower the landing gear. And I can listen to what they're saying. I'm not supposed to talk, but at 300 feet before we touch down, that's when he lowers the landing gear. But right before that, I heard him say to the commander, Dick, when I turn my head, the whole instrument panel's spinning. And the commander said, well, don't turn your head. Well, I'm down there and I couldn't help it. I pushed my button and I said, Ken, close your eye. And he did, and it stopped all the spinning. So after, they asked me to brief the whole astronaut corps, 100 astronauts. So I told that story, and when I finished, Mario Runco, an astronaut who'd flown several times, stood up, and he said, it's interesting, on his mission, everyone had vestibular problems coming in except him, but his job was to film the reentry through the camcorder. And so he had one eye closed. So there is something to it, and now other people have used that coming in to land the shuttle. Okay, wrong button here. Okay, so that's just showing you what I just talked about, and I'm going to skip by this. So what's up there now is the International Space Station. It's going to be decommissioned, and I don't know if any commercial group will pick it up or not, probably not. But anyway, we want to one day go to Mars, and I say not in the near future because there are many medical issues we've got to be able to understand how to tolerate. On a trip to Mars, everything has to be reused. We can't bring enough water. And, when I was chief scientist, and this is in 1994, I was in my office, and a friend of mine walked up to my office door, and he said, Larry, are you thirsty? And I said, no. And he said, you got to try this. This water's delicious. So he had a glass of water. So I drank some. I just drank his urine that had been purified. And so that's what we do now on long missions. We have to learn to reuse everything in order to have the capability to go, 40 million miles away to Mars. Anyway, that just tells you Mars is a pretty hostile environment, and so when we get there, we're going to have to build these habitats. And right now, NASA has these, I know you do 3D printing here, NASA has crane-like 3D printers that can build habitats that we can live in. And we're going to launch those in pieces, and then robotically they'll be put together before the people actually go to Mars. So that's the future plans of going there. Now, we're going to go there in this capsule, the Orion capsule. It's about 15 feet in diameter and 12.5 feet high, and 4 people are going to be in that, and it takes about 5 months when Mars and Earth are, you know, in what's called perihelion, they're close together. So 5 months to get there, right? So 5 months in that capsule with 4 of you. When you get there, you got to make fuel. You have to wait till the planets come back close together. So a whole trip to Mars and coming back takes 2.5 to 3 years. So you better like each other, that's for sure. So you all know about the James Webb Telescope and amazing images we've seen from it. And it's in a special region, Lagrange point, and so that we basically don't have to worry about it, you know, falling back to Earth or anything like that. But it's farther out, you know, some 1.5 million kilometers, as you see, from Earth, and it gives us these incredible images and let us look further into space than we ever have. This is one of the first images from the James Webb, and you know, if you look and see those kind of curved light areas, that's from galaxies. The light from a galaxy that's maybe 100 million light years away that's being bent by either other galaxy clusters, and so it's called gravitational lensing. The first person that described this kind of capability of light to be bent by gravity like that was Albert Einstein. And it actually focuses eventually into a ring, and it was named Einstein rings. And so that's sort of what it would look like. Well, one of the big missions that NASA has always had, and still has, is to look for life elsewhere. You probably all know we've now discovered really tens of thousands of exoplanets. And the question is, how can we see which of those planets has the capability to support life? Well, I think one of the new projects NASA is working on is one of the best ways to do this. So imagine on the far left is a star with planets around it, exoplanets. There you see our sun in the middle, and there you see Earth lined up in a straight line behind the sun from that other star. Now, if you go further to the right, the light from those exoplanets will be bent through gravitational lensing by our sun, and it doesn't focus to a point the way you'd like a nice telescope to do it. It focuses into the Einstein ring. So we would have to have several telescopes in that ring-like area, and you combine the images from those with a special technology that NASA right now at the JPL lab, they're working on this right now as I speak. And with that, you will be able to see on those exoplanets rivers, mountains, even large cities if there were people there. So, sounds great. You think, why don't we do that immediately? Look where those satellites are. Look up high. It says approximately 650 astronomical units. They have to be that far away for any exoplanet we want to look at, because truly the light coming in is more parallel. So everything's going to focus about 650 astronomical units behind Earth. So right now, with solar sails, we can travel 3 astronomical units in a year. Theoretically, we can travel with lasers maybe up to 20, 25 astronomical units in a year. Now, you'll be able to see this happen with that kind of technology. So right now, there's a group that, again, the JPL lab, working on this technology, and it's if I were head of NASA, I'd be spending a lot more money on this. But anyway, that's what they're doing right now. And I'll skip that. So now just some pretty images. Since I'm an Italian American, there's that part of Italy. And And, you know, lightning in space was a flashball. It looked like a flashball going off, and it was a chain reaction. Over South America, there were huge thunderstorms, and I would see one flash, another, right across the whole continent of South America. It was just mesmerizing to watch that. Again, just the sunrise. And this is a close-up, not with the naked eye, of the end of the Nile River and the Suez Canal. And there, look at those are the Canary Islands. See how blue they are. And way up at the top is the northwest coast of Africa. And this is the same storm. Sorry about the image, but this was taken with film back when I flew. I took this shot. It's coming off the coast of Saudi Arabia. We saw that on the first day, and 14 days later, you could still see the trail of it all the way across the ocean over Cuba. So again, when you hear about an oil spill on one side of the world, we don't all work together to clean it up, but it eventually affects everybody. Well, there's Mad Dog Mead, an amazing jet pilot, taking a bath in space. You know, Carl can squirt that bottle of no-rinse shampoo on his head, just lather up, and then we just dry off with a towel. When I was chief scientist, we were designing a shower for the space station. Because it's nice, you know, we didn't have the shower on the shuttle. But imagine, you get in this thing, this is with the design we had, you turn on the water, you know, it hits you, the water's not going to follow the floor, so pretty soon you're soaping up and you get a bubble of soapy water over your whole body. Now you could be like a dog and shake and some of it would fly off and stick to the wall, but the way we decided to dry off is with a vacuum cleaner. You had to suck the water off. Maybe that's why they didn't approve it. I don't know. It never ended up flying. The food comes in trays like that. We even had chicken soup. That's the bottom left tray there. You can dip your spoon in upside down, pull it out, and you got a bowl of chicken soup on it. None of it comes out, even though there's liquid in those trays, because it's hard to see it. But again, there's that sharp corner, that pinning edge that stops the liquid from going over the edge. In the can that you see, the pop-top can, that's the first thing I ate when I got up in space. It's butterscotch pudding. And so everyone else, some were puking, I was eating. And I went for that, and I forgot what NASA taught me. In space, you have to do things slowly. And I just popped the top. Well, there went my butterscotch, and it splattered all over the wall. So I was cleaning the shuttle. And okay, this is the most important slide, and this is one time I promised gravity is a big advantage. So what you do is you sit down on that commode area, and you see the two blue things. You pull them up, they're spring-loaded. Pull them over your legs. When you let go, they squeeze you down into the seat, so you make a real good seal. And then on the lower left side, that ball that you see, push it forward, and it turns a vacuum on through the commode. And I'm sorry, that's all I ever say. You have to use your imagination. Well, we were supposed to come home in 13 days, but because of Hurricane Darby, right over Edwards Air Force Base where we landed, we had to stay up an extra day. So now all the science was put away. This is when, you know, you see astronauts fooling around. I actually slam dunked a basketball that last day. But anyway, now, you know, I had slept 3 hours a night for the 13 days. I would go to sleep, but, you know, someone on the night shift, we worked in 2 shifts, would slam the door and would wake me up. And once I was awakened, I was so pumped I couldn't go back to sleep. So I was very tired. That last day, now that everything was done, the science was put away, I was pretty relaxed. And at one point, I went down to use the bathroom, and the commander was in the bathroom. And so I was just floating in the middeck, waiting for him to come out. Well, I fell asleep. And in the middeck, there's a cabin fan that cleans the air. I'm like a big sail, right? So while I was sleeping, it blew me backwards into the airlock where we keep all the dirty laundry. And it was about 3 hours later, you know, one of the crew said, "Where's Larry?" So everyone went looking for me. Unfortunately, this is the way they found me, sound asleep in the airlock. So I have this in my office, and it's signed by the commander. It says, "Larry DeLucas, hard at work on STS-50. And it turned out we couldn't land in California because of that hurricane. So we ended up having to land in Florida, but it's kind of neat. You know, NASA is always trying new types of material. And the reason we always used to land in California is the runway is dirt, so it's better for the tires. In Florida, it's a cement runway. And so they had tried a new type of rubber, and we landed. There was no damage to any of the tires, and as a result, because of our mission, Florida became the primary landing site, so we didn't have to ferry that shuttle back after every future shuttle flight. And so that's it. And if we've got time, I'd be happy to answer any questions. Don't be shy.